Welcome to Collapsed Latents, this week in AI, where we don't just report on the latest breakthroughs. We dissect them, we understand them, and we show you why they matter, not just for researchers, but for every creator, developer, and curious mind shaping the future. This week, 5 papers, 1 theme: intelligent simplicity. Not more layers, not more complexity, but smarter design, deeper reasoning, and systems that think, adapt, and run everywhere, from your phone to your browser. Let's dive in. #1. TWINFLOW, one-step image generation, the physics of speed. Imagine generating a high-resolution image in a single step. Not after 16 iterations. Not after 100. Just one. It sounds like magic. But TWINFLOW makes it physics. For years, diffusion models have relied on iterative denoising, step-by-step refinement from noise to image. Each step adds time, cost, and latency. Fast inference meant sacrificing quality. Quality meant waiting. TWINFLOW flips the script. Instead of learning just the forward path noise to image, it learns 2 trajectories, one real, one synthetic. Here's the insight: symmetry and velocity fields. The model learns not only how to go from noise to real data, but also how to go from noise to its own generated output. Think of it as training a mirror. The model learns to fail intelligently so it can succeed faster. Using a clever time reversal trick during training, TWINFLOW minimizes the difference between the velocity fields of these 2 paths. The result? A smooth, direct trajectory from random noise to final image. No iteration required. And the architecture? Clean. Minimals. No distillation. No frozen teachers. No GANs. Just one model, one objective, end-to-end. When tested on QNImage20B, a 20 billion parameter model, TWINFLOW achieved 1 NFE performance with a Gen Eval score of 0.86, nearly matching the original model's 0.87 at 100 NFE. That's a 100 times speedup with negligible quality loss. But here's what's most impressive: diversity. Unlike distillation methods that collapse into repetition, TWINFLOW preserves rich variation across seeds. Each image is unique. Sharp, detailed, natural. This isn't a shortcut. It's a principled solution grounded in dynamical systems theory, where the path from noise to data isn't a random walk, but a learned manifold shaped by symmetry and self-consistency. TWINFLOW doesn't just accelerate generative AI. It redefines what's possible in a single step. #2. VideoCoF, where AI thinks before it edits. Now let's talk about video editing. Not the messy, mask-heavy, frame-by-frame grind, but intelligent editing, where the AI sees, reasons, then acts. Enter VideoCoF, not just a new tool, but a new paradigm: chain of frames. You give it a simple instruction: remove the red car from the parking lot. Instead of guessing, the model first generates a reasoning frame, a soft, grayscale heat map that highlights where the edit should happen. This isn't a mask. It's a learned pointer, a spatial attention signal trained to identify the target object's location and context. Only after this reasoning step does the model perform the edit, with precision, coherence, and 0 manual input. But the real breakthrough is temporal reasoning. Most models fail on long videos because their row P, rotary position embeddings, degrade over time. They lose track of sequence order. VideoCoF solves this with a novel row P alignment strategy. It resets the time indices so the reasoning frame stays anchored at 0, while the target video's timeline restarts. This preserves the model's ability to reason across long sequences. Result: 4 times longer generalization. A model trained on 33 frame clips can edit 141 frame videos, smoothly, coherently, without artifacts. And the data? Just 50,000 video triplets, source, reasoning, target, generated using AI to detect, mask, and edit objects. No need for million video per training. The results: 15% better instruction following, 18% higher success rate than models trained on 1M+ videos. In multi-instance removal, it removes only the intended object, no accidental deletions. In style transfer, it edits only the largest cup, no confusion. No hallucinations. No errors. VideoCoF isn't just editing. It's AI that understands context, spatial relationships, and intent, all without a single mask. It's reasoning as a first-class citizen in the generative pipeline. #3. M-NISP, your phone's hidden photo lab. Now let's talk about your photos. That sunset you took last year. The one that's flat. The one where the sky's too blue, or the skin tones are washed out. You're not imagining it. That's auto-white balance, and it's often wrong. Worse, once you save it, you're stuck. But what if you could re-edit that photo years later, with full creative control, even after it's been saved? Enter modular neural image signal processing, M-NISP, a revolutionary system from Samsung's AI Center in Toronto. This isn't just a new photo editor. It's a complete rethinking of how phones process images. Instead of a monolithic black box ISP pipeline, M-NISP breaks it into modular neural stages: denoising, color correction, tone mapping, chroma mapping, and detail enhancement, each a separate, learnable neural network. You can swap, upgrade, or retrain one module without touching the rest. It's like having a kitchen with modular ingredients. Change the spice, adjust the heat, or invent a new dish, all without starting over. And here's the secret. Raw data is embedded inside the final JPEG using smart compression. When you save a photo, you're not just saving an image. You're saving the original scene, ready to be re-edited anytime. Want to adjust white balance? Choose neutral mode for accuracy, preference mode for natural warmth, or manual temperature tint controls for full creative freedom. Need more contrast? A single slider. Want sharper details? Intelligent sharpening that only hits edges, no noise amplification. Each module is trained independently, ensuring stability, interpretability, and easy debugging. They even tested it on unseen devices, iPhone X, Galaxy S9, and it worked like a pro. With only 500,000 parameters, M-NISP outperforms commercial photo editing software. This isn't just about better images. It's about freedom, the freedom to re-edit, experiment, and bring old memories back to life, with the same quality as the first time. #4. DUVER AI agents that debug themselves. Now imagine running a team of AI agents, planning a trip, researching history, debugging code. The system completes. The answer comes back. But it's wrong. How do you find the one flawed step in a 100-step conversation? Traditional debugging. Feed the log to another LLM and ask, which step failed? But here's the problem you're guessing. Studies show accuracy is below 10%. Enter DUVER, a framework that doesn't guess. It tests. DUVER's philosophy, do then verify. Instead of diagnosing, it repairs. Here's how it works. 1. Hypothesize a failure point. The web surfer didn't scroll to the bottom. 2. Intervene, rephrase the instruction. 3. Rerun from that point. 4. Check, did the failure disappear? If yes, validated. If no, refuted. If the agent still can't follow the instruction, it's not a diagnosis flaw. It's a capability flaw. This turns debugging into scientific validation, not speculation. Tested across multiple frameworks, Magnetic One, MathChat, DUVER recovered 18% to 49% of failed trials, even with open-source models like QN3-8B. And it surfaces bottlenecks. The agent can't scroll to the bottom, so you add a new tool. It can't parse PDFs, so you improve handling. DUVER isn't just a tool. It's a closed-loop system for self-improving agents, where debugging feeds back into the system. This is how we move from fragile, brittle AI to robust, reliable, self-correcting systems, the foundation of trustworthy autonomous agents. #5. Visionary, the world model carrier for the web. And finally, the most mind-blowing of all. Imagine opening your browser, typing a URL, and instantly stepping into a photorealistic, interactive 3D world. No install, no drivers, no GPU setup. That's Visionary, a web-native platform built on web GPU-powered 3D Gaussian splatting, designed to be the universal runtime for next-gen world models. Why does this matter? Because traditional 3D viewers are either heavy desktop apps or slow WebGL viewers. Visionary runs entirely in your browser, using WebGPU, the modern, high-performance API that unlocks GPU acceleration in JavaScript. But the real innovation. Per-frame ONNX inference tightly coupled with rendering. Every frame an ONNX model, a portable framework-agnostic neural network, generates or updates Gaussians in real time. This means neural avatars that deform with your body pose, 4D dynamic scenes that animate with temporal consistency, style transfer networks that enhance visuals on the fly. All inside the browser. No native code. And performance, 135 times faster sorting than WebGL-based viewers. Frame time under 2 milliseconds. No popping. No streaking. Just smooth, correct rendering, even during rapid camera motion. Visionary also supports depth-aware compositing. Gaussians are properly occluded by meshes. It handles generative post-processing like diffusion denoisers, all in browser. Benchmarks. On a 6M Gaussian bicycle scene, Visionary outperforms Spark.js in both speed and image quality. And it's open source. It's a 3JS plugin. You can embed it in any web app, your research demo, your virtual gallery, your interactive editor, with zero shader rewriting. Visionary isn't just a viewer. It's a world model carrier, a unified platform for reconstructive and generative 3D content built for the web. Future. Physics engines. Sim-to-real transfer. 3D agents grounded in language models. But for now, the future of spatial AI starts with a single URL. So what's the big picture? This week we've seen a unifying theme, intelligent simplicity. TWINFLOW uses symmetry to replace complexity. VideoCoF teaches AI to think before it acts. M-NISP gives you control by breaking the pipeline into modular pieces. DUVER turns debugging into repair, not guessing. And Visionary makes the entire 3D world accessible in your browser. These aren't just incremental improvements. They're paradigm shifts, moving from black box systems to transparent, scalable, and self-correcting AI. The future isn't about more models, more steps, or more complexity. It's about clarity, control, and coherence, even at scale. So if you want to see these tools in action, like, subscribe and hit the bell because next week, we're diving into AI agents that write their own code. Until then, keep creating, keep exploring, and keep pushing the edge. This is Collapsed Latents, This Week in AI. Stay curious, stay bold, and stay ahead.